Thank you very much for your kind introduction. So my name is Taiji Suzuki. So I'm from the University of Tokyo, and I'm also the team leader of deep learning theory team in the AIP weekend. So today, I want to talk about deep learning theory and optimizations. Okay. So what I will talk in this tutorial is a bit theoretical side. So there appears many mathematical equations, but I will try my best to explain them in an intuitive way. So okay, so I guess many parts of you are a kind of application side, and some part of you are a kind of theoretical side. So this is a little bit for the theoretical side guides, but yeah, I will try my best to explain all of them, so that everybody can be and can understand the contents. Okay, let's start. Okay, so as you know, so the deep learning has been very successful in many applications. For example, it is used in AlphaGo, and also deep learning is applied to many pattern recognition tasks. And in particular, in the pattern recognition tasks, so without deep learning, it is almost impossible to achieve the state-of-the-art performances. And also, it is applied to some image generation and image transformation. And so we have seen many success. So in addition to such an AI type applications, so it has been applied to many other fields like quantum chemistry, and it is used to predict the molecular properties by using graph convolution neural network. And it is also applied to protein structure prediction. Okay. For example, so the AlphaFold won the CASP13 and the CASP14, and the performance was much better than existing other methods. So, and nowadays we also have very huge language models, and so it is beginning. It is beginning to be able to do some logical reasoning by using this kind of language models. So we have seen the great improvement of the methodologies, and we have seen the much development of such a deep learning applications. Okay. So despite of its success, the great success in many applications, so but its theoretical understanding is not so good. So we haven't understood completely why the deep learning works well in practice. Okay. So there are too many hypotheses, and so this technique is effective and this technique is effective. So there are not so unifying theories. Okay. So there are some individual hypotheses, but there are no a kind of a systematic understanding about so all hypotheses. So we need some unifying theories to understand the deep learning, to understand why deep learning works well in practice. Okay, so in particular, we need some understanding of the principle of deep learning. Okay? So in addition to the understanding individual techniques, we need some unifying understanding of the principle of deep learning. Okay? So then, by doing so, maybe we can find the essence of the good learning systems that makes the learning system makes learning system very very powerful. And through such an understanding, maybe we may find a new method that could be beyond the deep learning. So this is why we need deep learning theories. Okay, so if we have some unifying understanding of deep learning, so then it could be useful and helpful to find a method that could be beyond the deep learning. And also the theories of deep learning has been demanded by many fields. For example, from the academic conferences, you see many deep learning theory papers, for example, in ICML, iClear, and NeurIPS, and of course in ACML. For example, so this is on Ali Rahimi's talk at NIPS 2017. So this is about the test of time award. And he criticized the situation of deep learning researches as alchemy. Okay. Well, so this is because there are too many experimental results without a theoretical background. So then he said the situation is like alchemy. Well, I personally think that the situation is not alchemy. So we need much more experiments. So because deep learning is a kind of a new field. So we need to find more possibility of the usage of deep learning. And of course, we need more we need more theories, but so before we can develop a new theory, so there should be many experiments. So I don't think it is an alchemy, but this is also one of the reasonable criticism to the situation of the deep learning researches. So that we need more theoretical understandings. Okay. So and in addition to that, the industries also has a demand for the deep learning theories because they don't want to use some black box system. Okay. So they want to use the white box system. So because they have an accountability of their product, so they need to give an explanation about the output from their product. Okay, so therefore, for that reason, so industry also needed to make the deep learning more white box. So then maybe deep learning theory would be helpful. Okay, so anyway, so to execute deep learning theory, so we need mathematics. So mathematics is very useful. So the situation is very similar to the situation, today's situation. So like the relation between the deep learning and the mathematics is very much like that between the physics and mathematics. For example, in 100 years ago. Okay, so about 100 years ago, so we observed many experimental results in physics that could not be explained by a classic physical theories. For example, the Newton mechanism. Okay, Newton mechanics. So there are many experimental results, but there are many new experimental results that could not be explained by classic theories. Okay, so to explain those new experimental results, so the many physics theories, new physics theories were developed, like a theory of relativity and a quantum mechanism. Okay, according to such a development, the new mathematical tools were also developed, like a Riemannian geometry and a functional analysis. Okay, so this kind of relation is very similar to today's situation between the deep learning and the mathematics. Okay, so we are observing many experimental results in the in a deep learning researches, but they could not be explained by classic statistical learning theories. Okay, so therefore, in addition to the machine learning researchers, the mathematicians, the physicists are joining to machine learning community, and we are developing new theories that can explain the behavior of deep learning, and also the new mathematics have been developed for that purpose. Okay, so in that sense, the relation between deep learning and mathematics is very much similar to that between physics and mathematics in 100 years ago. Okay. Okay, so and also the deep learning theory could be divided into these kind of levels from application to foundations. Maybe the most application side, so there could be the interpretability. Okay, so in this level, so we give some explainability to the individual output for each instance. Okay, for example, in the industry, so they have accountability. So they need to give an explanation about why some output comes from their product. Okay, so they need accountability, and also some visualization is also useful, and by doing so, maybe their product could be much easier to maintain. Okay, and so in this category, so the technique so-called XAI is coming in. Okay, so such a technique is useful in this level of the theories. Okay. Okay, the second level is the analysis of similar techniques. Okay, so there are many techniques such as a dropout and batch normalization, layer normalization, and so on. So there are many small techniques that can enhance the performance of deep learning. So then, so there are many theories to explain why such an individual techniques are effective in practice. Okay, so that is the second level. The third level is a little bit more fundamental questions. Okay, so this is about the principle of deep learning. Okay, so maybe in this level, so we don't need to take care of individual methods, but we investigate the principle of deep learning that can explain so why deep learning works well in practice. Okay, so we investigate the essence of deep learning here. So and then more deeper or more fundamental levels, so there is an essence of learning. So in this level, so we can forget the deep learning. Okay, so we investigate the more general learning system, and we characterize so what is the essential for the good learning systems. Okay, so we develop some kind of unifying theory for good learning systems. So including deep learning, but also so we can also consider so any other methods. And then through such a learning theory, so maybe we can find some key to find methods that can beyond the deep learning. Okay. Okay. And today's topic is around here. Okay. So basically, I will talk about some theories about the principle of deep learning. Okay. And I will also talk something about the theories of individual technique and something about the essence of learning. But basically, so I will talk about the principle of learning, the principle of deep learning. Okay. So I will talk some theories around here. Okay. So the principle of deep learning theories can be roughly divided into these three categories. So one is a representation ability. The second one is a generalization ability. The third one is a optimization ability. Okay. In the representation ability, so we will investigate the functional approximation ability of neural networks. Okay, the neural network, deep neural network is a kind of functions. Okay, so that represents some input-output relations. For example, in a classification task, the input is an image, and the output is its category. Okay, so then, to perform some classification tasks, so we need some functional approximations. Okay, so suppose that there is a true input-output relation. So we want to realize that by using a deep neural network. So the question is, so how accurately we can approximate such an input-output relation by deep neural network? So then we need to investigate such a functional approximation ability. Okay, so that kind of investigation is coming here. And the second one is the generalization ability. Okay, so but in practice, so we needed to estimate such an input-output relation by using a finite number of data points. Okay, so even though the neural network can approximate any functions, but we need to estimate that by using a finite number of data points. So there is some gap between the finite number of training data and test data. So we should bridge this gap. So then there appears the generalization ability. Okay, so we need to generalize the finite training data points to the test data. Okay, so then such a generalization ability analysis is coming here. So this is a kind of one of the main topics of statistical learning theories. Okay, so the third one is optimization ability. Okay, so it is well known that the optimization in deep learning is highly non-convex. So it is not trivial that the gradient descent or stochastic gradient descent can find a good global optimal or good local optimal. So we need some theories to ensure that such a method is effective to find a good solution. So such analysis is coming here. Okay, so I will talk in this tutorial. I will talk these three categories so one by one. Okay. So this figure shows the relation between these three categories. In the representability analysis, so we investigate, so basically the distance between the true function and the deep neural network model. So how closely the deep neural network model can be to the true function. Okay. So we investigate this functional approximation ability in this category. And basically, we want to find this closest point by using the finite training data points. But there exists some sample deviation. So the estimator has some variance. So in the generation ability, so we bound this variance. Okay. And moreover, so to obtain this estimator, so we need to execute some optimization. So then we need to ensure that some optimization technique can find the good estimator. So such analysis is categorized in the optimization ability category. Okay. Okay. So then, so this is a table of this tutorial. Okay. So first, I will talk about the representability, and next I will talk about generalizability, and then we are going to optimize ability. So today I will be able to talk about I will be able to talk until this category so by here. Okay. So okay. So anyway, so let's go into the first category, the representability. Okay. So when we talk about the representability of a deep neural network, so maybe it is most important to say that it is a universal approximator. Okay, that means that the neural networks can approximate any functions with any precision. For example, to rigorously state this kind of claim, so we need to define any function or any precision in more rigorous way. For example, so any function means that any function in the L2 space or any function in a continuous function space, something like that. So any function is in more precisely, it is like a L2 norm or uniform norm and so on. But anyway, so roughly speaking, we can say something like that. So actually, so by using the infinitely many neurons, so we can approximate any function. So if you have many neurons, so then the neural network can approximate any function. So and therefore, if you have infinitely many computational resources, so you can realize any input-output relations. So you can solve any tasks. So basically, so you can solve any task by using deep neural network. So if you have a sufficiently rich resources. Okay. So behind this theory, so here is the one intuition. Okay, so remember that the Fourier transform can be given like this. So if f hat is an Fourier transform of function f, so then the inverse Fourier transform can be given like this. Okay, so this means that the function f with some integrability properties can be expressed by a superposition of the cosine and sine functions. Okay. So exponential I that omega transpose x can be decomposed into the cosine function and the sine function. So, and we can see that the function f can be represented by the sum, basically the summation of the cosine and the sine functions. The same thing also happens for the neural network. Okay, so instead of cosine and sine, so you can use an activation function. Okay, so by taking a superposition of many neurons, so you can reconstruct any function. Okay, so this is very much analogous to the Fourier transform. Okay, so instead of exponential, so I omega transpose x, so we use the output from each neuron. Then we take its superposition like this. So this is very much similar to Fourier transform. So therefore, we can say that the two-layer neural network is a variant of a Fourier transform. So the practical finite width neural network can be seen as a discretization of this integral. Okay, so this is one intuition of a two-layer neural network. Okay, so here is an illustration of universal approximability. And suppose that we have these data points. So behind these kind of data points, so there is a true function. The true function is represented by the conditional expectation of y given input x. Okay. So the true function looks like this. So we want to approximate that function by neural network. Okay, so now we use ReLU activation and we consider two-layer neural network. So if the internal node has one neuron, so this is just one neuron two-layer neural network, so then the fit could be like this. Maybe we have this kind of fit. And so you see, so the fit is a little bit good around here, but it is not good around here. So it doesn't give any explanation about here, around here. So therefore, we need some more neurons. So therefore, we add another neuron. So then we get a better fit. So the fitting becomes much better. But this is not a completely good fit. So we add another neuron, so then we get this fit. So this looks much better. And by repeating this procedure many times, finally you get this kind of very smooth functions. So although the ReLU activation function is not a smooth function, so by taking a sum of many ReLU activation functions, so we get this kind of a very smooth function. Okay. So eventually it can approximate this kind of smooth function. Yeah. So this kind of notion can be rigorously formulated. For example, so these classic papers have shown that the two-layer neural network is a universal approximator. So more precisely, for example, the set of a two-layer neural network is dense in the L2 space or the continuous function with compact support or something like that. Okay. So here is the most famous theorem of universal approximability of neural networks. I guess the Cybenko's theorem is most popular. So I state the formal statement of the Cybenko's theorem here. Okay, so here we assume that activation function sigma is a sigmoidal. The sigmoidal activation function is defined like this. Okay, so activation function sigma x goes to 1 as x goes to infinity, and sigma x goes to 0 as x goes to minus infinity. So the sigmoidal function is one of the sigmoidal function. Okay. So the sigmoidal function goes to 1 as x goes to infinity, and the sigmoidal function goes to 0 as x to minus infinity. But it is not restricted to sigmoidal functions. So the activation function can also decrease. Okay. So we don't restrict ourselves to a monotonically increasing function, but the sigmoidal activation function can decrease like this. So anyway, so if the activation function satisfies these conditions, it is called sigmoidal. Okay, so now we assume that the activation function is continuous and sigmoidal. So then for any function f, which is continuous on some compact support, and any precision epsilon, so there exists a finite width network like this, such that and the L infinity node between the function f and the neural network is bounded by epsilon. So therefore, so this is the more precise definition of the statement of the universal approximability of neural networks. Okay, so any continuous function with compact support can be approximated by a two-layer neural network with any precision in terms of the L infinity node. So moreover, it is known that the set of the continuous function is dense in the L1 and L2 space. So this theorem also states that the neural network, the set of the neural networks is dense in the set of L1 and L2 space. Okay. And so here, so the ReLU activation function, so the ReLU activation function is very popular nowadays, and the ReLU activation function does not satisfy these conditions, but taking summation of a ReLU activation function, so we can construct this kind of a function, okay, by taking sum of the neurons with ReLU activation, so you can construct a sigmoidal function. So therefore, ReLU activation function also satisfy this universal approximability property. Okay. Okay, here is a proof outline, but I skipped that detail. So if you are interested in, so please look at this one. Okay, so as I said, and there is also a kind of a variant of a Fourier transform behind the neural network. Okay. So I don't go much into I don't go into much details about this theorem, but I briefly explain that. Okay. So this is called the dual Dirichlet transform. So eta is an activation function. Okay, so by taking some integral with respect to the parameters of the neurons, we can recover the function value of fx. So here t is the weight of the weight of the parameters and a at b. Okay, so this weight is obtained by the so-called Dirichlet transform that is given by like this. So this is a very much analogous to the Fourier transform. Here, the psi is a so-called dual activation function. So that satisfies so-called this admissible condition. Okay, so eta is a given activation function. So according to an activation function eta, so we pick up one. So we pick up any dual activation function psi. So psi it can be anything. So psi can be any function. So if it satisfies this admissible conditions. Okay. So any function is okay. So as long as this admissible condition is satisfied. So anyway, so there. So suppose that there exists some dual activation function psi. So then, by taking a kind of convolution to the target function f, so we obtain a Dirichlet transform, and this Dirichlet transform is coming here. So then we perform the dual Dirichlet transform. So then you can recover the function value fx like this. So here k is some constant, so you can neglect this one. Okay, so first you apply the Dirichlet transform, and after that you apply the dual Dirichlet transform. So then you can recover the original function value. Okay. So this is very much analogous to the Fourier transform and the inverse Fourier transform. So you can see that the two-layer neural network you can see that the two-layer neural network is a kind of a Fourier transform. So where instead of cosine and sine functions, the activation function, non-linear activation function is used. Okay. But yeah, so this gives us some good intuition about the neural networks. Okay, so so then we have known that neural networks has a universal approximability property. But in terms of a universal approximator, the kernel method is also a universal approximator. Okay, so but in practice, so instead of the kernel method, nowadays we are using deep learning. So why it is? For example, in the ILS RC competitions, so after 2012, the deep learning has won the first prize. So nowadays it is very difficult to get the state-of-the-art performance using the kernel method. So therefore, in the pattern recognition tasks, so everybody is using deep learning. So why is it? So maybe so you are not so much familiar to the kernel method. So you can see the kernel method like this. Okay, so this is just a rough intuition of the kernel method. The kernel method is roughly speaking a two-layer neural network. So, but the difference from the usual deep neural network model is that in the kernel method we fix the first layer's parameter. Okay, we consider a two-layer neural network, and also in the kernel method, the internal layers can be infinitely wide. Okay, so the number of neurons in the internal layer can be infinite. So that is an interesting point of the kernel method. But anyway, so it is just a two-layer neural network. However, the first layer's parameter is fixed. So this is a kernel method. So because we fix the first layer's parameter, so this is just a linear model. Okay, so we only train the second layer's parameter. So this is just a linear model. So yeah, so this is called the kernel method, a kernel model. Okay, on the other hand, in the deep neural network models, we can train the first layer's parameter. Okay. So this maybe so you think this difference is very small, but this difference makes a huge gap over the performance of learnability. Okay, so this is a significant difference. So just a 1 layer difference has a much impact to the performance. So of course, for the deep neural network models, you can consider much deeper models But anyway, so in the deep neural network model, so you can train the parameters in all layers. So this means that in the deep neural network model, so you can train the feature extraction layers. But in a kernel method, so we don't train such a feature extraction layers. We only train the last layers parameter. So that gives a much difference. So from now on, so we compare the accuracy of estimation and approximation abilities of kernel and the deep models, and we compare the performance of these methods. Okay, so first we consider the explicit power of deep neural network models. So there are many definitions there are many mathematical definitions of the explicit power of the models. And so anyway, so these papers, all of these papers concluded that the deep neural network model has an exponentially large power of the expressive power expression against the number of layers. So that means that if you increase the number of layers, so then the explicit power of the model increases in an exponential order. So it is not a polynomial order. So the increase of the explicit power is an exponential. So therefore, the deeper network is more efficient to approximate some target function than the shallow networks. Okay, so here is one intuitive result from this paper. Okay, so let us consider deep neural network with depth L and width W. Oh, I have one question. So slide 21. What is the motivation benefit behind keeping the initial layer fixed in kernel models? Okay. Yeah, so this is because we want to make it linear. So for example, in the deep models, so there appears many nonlinearity. Okay, so in terms of the first layer, so this is highly nonlinear. Because of that, the optimization becomes non-convex. Okay, so now I'm talking about just approximation ability and the statistical properties. But if you are considering optimizations, so the linear model is much easier to handle. But if you use a deep model, so the optimization becomes highly non-convex. So we want to avoid such a non-convex optimization. But on the other hand, so in the kernel models, the kernel method, by fixing the first layer's parameters, the optimization problem becomes convex if the loss function is convex. For example, the squared loss or logistic loss, so then the everything becomes convex. So and also, so we can use many theories of linear models to analyze the kernel models. So therefore, the kernel method has been used in many applications. So yeah. Okay. What the global minimum in deep models? Okay, so the global optimality of a deep neural network model is another interesting topic. So I will talk that tomorrow. Okay. So today I will not talk about much about optimization. So tomorrow, so I will talk about some theories of optimization of deep models. So one ingredient is that if you consider very wide neural networks, so then the gradient descent of gradient descent for deep neural networks can likely to find the global optimal. So yeah, so that is the one answer. So if you consider very wide neural network, so then the gradient descent can find the global optimal. Okay, so thank you very much. Okay, so let's go. Okay, so let us consider a very deep neural network with depth L and width W. Okay, now we try to approximate this deep neural network by shallow network with depth L prime. And so the depth L prime is fixed. So the question here is how large this shallow network should be to approximate the target network. Okay, so the constraint is that the depth L prime is much smaller than the original network. So then the question is, the answer to this question is that the width should be as large as this quantity. So L prime times W to the power of L divided by L prime. So for example, if L is like a 20 and L prime could be 2 or something like that. So then L divided by L prime is just a 10. This is just a 10. So this means that, so there appears W to the power of 10. So this could be huge. For example, if the width of the original network is 10, so then this could be 10 to the power of 10. So that is tremendously large. Okay. So anyway, so there appears an exponentially large width. So to approximate the target neural network, so by shallow neural networks, it requires exponentially large widths. Okay, so this means that this means that the deep neural network is exponentially expressive. But to realize that function by increasing the width, it requires an exponentially wide network. Okay. So therefore, instead of increasing the width, so increasing the depth is more efficient in terms of the explicit power. So yeah. So here's another example. Okay, so let us consider a mean field model, so defined by some probability measure pi. So here let us consider the unit sphere on the d-dimensional Euclidean space that is denoted by st1 minus 1. And so the pi is a probability measure on the unit sphere. And so according to this probability measure pi, so we define the mean field model h pi like this. Okay, so W is a parameter of the first layer. Okay. For each parameter W, so we define a weight AW. So AW is the weight of each parameter W. And then we take its integral with respect to the probability measure pi. Okay, so sigma is on some residual activation functions. So okay, for each parameter W, so we put a weight AW like this. And we assume that this weight satisfies this integrability conditions. The square of AW satisfies this integrability condition. So that means L2 norm of AW with respect to the probability measure pi is finite. Yeah, we consider this function class. So you can see this is a kind of a neural network, but instead of considering a finite width, we consider the integral. Okay. So that is a difference from the usual neural network. Okay, so now we try to approximate a function in this class by a finite width neural network. Okay, so instead of integral, so we consider the finite width. Then, so the question is how large this finite width neural network should be to approximate this target function. Okay, so I have one other questions. Can you explain the use of the terminology mean field? Is it related to some theory from another field? Oh, okay. Yeah, so this is coming from physics. Okay, so in the mean field, so I'm not an expert of the physics, but in the physics, so we consider a system where we have many particles, like gas or something like that, and we have many particles. So then in the physics, like a statistical physics, they analyze the behavior of the gas. So then the behavior is something like a, how to say, so some behavior on such a many particle system can be written by a kind of integral. Okay, so then this is so then there is some connection between the neural network and such a mean field analysis. So this is also called a mean field model. Yeah, more precisely in a neural network, in the neural networks, in the literature of the neural networks. So taking an average of the output from each neuron is so-called mean field regime. Okay. So there are many there are many possibilities of the scaling of the parameters, but in the mean field regime, so we take an average. Yeah, so suppose that there are many neurons and we take its average, so it is called the mean field regime. But if you consider another scaling, like we take the summation of the new output of the neurons, and we take we multiply it by like 1/square root m. So where m is the width. So then it is not called a mean field regime. So then in that sense, this can be seen as a mean field model. Okay, so is it okay? Okay, yeah. Okay, so then now we try to approximate this kind of integral by using a finite width network where width is m. Okay, so you can tune both first and the second layers parameters. Okay, so the approximation error can be bounded by like this. The squared L2 distance between f and f hat is bounded by 1/m. So this is reasonably good. So if you increase the width, then the approximation error becomes better. Yeah, so this is reasonably good. But what happens if you fix the first layer's parameter? Okay, so in this neural network model, so you can tune both the first layer and the second layer's parameters. But what happens if you fix the first layer's parameter? The answer is something like that. Okay, so let us consider the so-called random feature model. So where we randomly generate the first layer's parameter and we fix that. So we don't train the first layer's parameter. We only train the second layer's parameter. So then the estimation, the approximation error is lower bounded by this quantity. So in some worst case error, in a worst case sense. So the error is lower bounded by 1/d squared times m to 2/d. So a problem is that d is coming here. So d is the dimension of the input. Okay, d is the dimension of the input. If the dimension d is very large, so then the rate of the convergence of this approximation error becomes very, very slow. Yeah. So for example, if you want to make this approximation error smaller than epsilon, so then in the neural network model, it is sufficient to set m to 1/epsilon. So just 1/epsilon width is sufficient. But for the random feature models, m should be exponential. So like epsilon to minus d. So epsilon to the minus d is required. So there appears an exponential dependency on the dimension d. Okay, so this is very large. Instead of 1/epsilon, so there appears 1/epsilon to d. So this is huge. So in particular for the high dimensional case, this is huge. So this is called the curse of dimensionality. So maybe so you consider the two-layer neural network and the kernel model is very similar. So the difference should be very small, but the difference is significant. You see a significant difference between this one and this one. So yeah. So even though this is only the two-layer network, so this is not a very deep network. This is just a two-layer neural network, but there appears a significant difference. Okay. So now, so we have seen that the neural network has a good representation power. Okay, now we are going into much more statistical properties. Okay, so we have considered a kind of approximation ability of neural networks. So now let us consider the estimation problem. So that means we want to estimate the true function from finite data points. So far, we haven't considered any estimation problems. Okay, so from now on, we consider a more statistical problem. Okay, so for that purpose, let us consider non-parametric regression problem where the output yi is given by f naught xi plus gzi, where xi is distributed from a d-dimensional unit cube, and gzi is an observation noise, which is a Gaussian noise. And so the output yi is obtained like this. So we want to estimate the true function f naught from finite data point xi yi from I equal 1 to n. Okay, so the situation can be depicted like this. The black dots are the training data points. So from those data points, we want to estimate this blue line. Okay, so the blue line is the true function. So this cannot be seen in the training phase. Okay, so we can only see these black points. From that black points, we want to estimate this blue line as accurate as possible. Okay, so suppose that we have an estimator f hat. So then as a performance measure, we employ the estimation, we employ the mean squared error, right? So this is the L2 distance between f hat and f naught. And we take the expectation with respect to the realization with n data points. Okay. So if this mean squared error is small, so then that estimator is good. So now, so we compare the estimation error between the deep learning and the kernel methods. So that is our purpose now. Okay, now before we are going to the analysis of a deep network, so I want to mention something about the classic statistical learning theories. Okay. I guess some of you have attended the tutorial by the Peter Bartlett, and I guess Peter Bartlett has already explained something on the classic statistical learning theories. So then you are already familiar to that, but I just very briefly explain that here. Okay, suppose that we have a model F, so which have a d-dimensional parameter. So F is characterized by d-dimensional parameter, and N is a data size. Okay, so as an estimator F hat, we consider this kind of least squares estimators. So that means in the models we perform this empirical risk minimizations where the loss function is a squared loss. We want to minimize this empirical risk. So then the empirical risk minimizer is denoted by F hat. So now we are interested in the predictive error of F hat. So that here the predictive error is just a mean squared error. Okay. So if F hat is very small, the mean squared error for F hat is very small, so then it has a good predictive error. So okay, so this predictive error is basically bounded by the variance and the bias. The variance is given by the dimensionality D. So D is the number of parameters of the model. So D divided by sample size N is coming here. Of course, we need some assumptions to have this kind of bound, but under some reasonable assumptions, so we have this bound. And as for the model bias, the bias is just given by the distance between the true function and the model. The true function. So here is the closest point to the true functions, and the distance between the true function and the closest point in the model is the model bias. The bias is coming here. So there appears some trade-off between the bias and the variance. So if you increase the complexity of the model, so then the dimension D becomes large, so the variance becomes large. But the bias could be smaller. So on the other hand, if you decrease the complexity of the model, so then the bias becomes large, but the variance could be smaller. So you see there is a bias and a variance trade-off. So you need to balance the bias and the variance to obtain the good predictive performance. Okay, so more precisely, and this can be written by like this in more mathematical rigorous way. Okay, so the mean squared error is bounded by the log of the covering number of the model divided by sample size plus the distance between the true function and the model. But I skip some details. Okay, so this kind of classic learning theory can explain the scaling law. So maybe you know the scaling law. So today we have very huge we have a huge language models such as GPT-3 and BART. Okay, so for that models we observe this kind of scaling law. Okay, so the horizontal axis is basically the number of the data points. The training data size is the horizontal axis. More precisely, log of the training size is coming here. The vertical axis is a log of the predictive error. Okay, we see that as the sample size going up, so then the predictive error goes down. The interesting point is that predictive error, the log of predictive error, goes down in a linear order. Okay, so you see a good fit of the linear function like this. So this is the predictive log of the predictive error is a kind of a affine function with respect to log n. Okay, so here you see there are many lines. So each line corresponds to the predictive error for a fixed model size. Okay, so if you fix out some model size, so then you have this curve of the predictive error. But by choosing the best model size for each sample size, so you get this linear fit. Okay, so yeah, linear curve. Okay, so more formally, so it can be written by like this: the log of the predictive error is given by minus some constant times log n plus constant. Okay, the slope is a linear function. Okay, so we tried to explain this by using a very classic simple model. Okay, so let us consider a linear model given by like this. This is a kind of kernel model. Okay, so here phi j is basis function case, and the true function f naught is the linear combination of these basis functions. So we consider this noisy observation model like this. And here we assume that alpha j, the coefficient of the true model, satisfies these conditions. Here mu j is some value, so like a j to minus a. And we assume that the summation of alpha j squared divided by mu j is bounded by, is finite. Okay. So this means that alpha j squared should decrease faster than j to the minus a minus 1. Okay. So then this means that so a controls the decaying rate of alpha j squared. So intuitively, the coefficient alpha j should decrease. So this series, this summation converges. So then alpha j should converge to 0. So then a controls how fast the alpha j decays to 0. Okay. So if a is large, so then alpha j decays rapidly, and if a is small, so alpha j doesn't decay so rapidly. So in that sense, a controls a kind of complexity of the model. Okay. Okay, to estimate this function, so let us consider the m-dimensional finite dimensional model. Okay, so we pick up top m basis function. So phi j is also coming here. We pick up m top m basis functions, and we fit this linear model to the data. So by considering this least squares estimation. Okay. So the coefficient alpha j is obtained by solving this least squares problem. Okay, so this is just an ordinal least squares estimator. So then by applying this result, this classic running theory, so roughly speaking, we have this bound of the predictive error. The predictive error is roughly bounded by the bias and the variance. The variance is obtained by the dimensionality of the model divided by sample size. And through some calculations, you can show the bias is like a m2 minus a. Okay. So remember that the model, the linear model is m-dimensional. So this is the m dimension. So m is coming here. The number of parameters is just m. And also the bias term is obtained by m2 minus a. So the a controls the bias. So if a is large, so the bias is small. If a is small, so the bias is large. So the decaying rate of the coefficient alpha j characterizes the bias. Okay. So anyway, we have this bias and bias. Okay, now we balance this bias and variance. So then the maybe optimal model size, the optimal dimensionality of the model could be like this, m to 1 over 1 plus a. So by substituting this optimal m to these expressions, you get the optimal rate of the estimation error like this. So n to minus a over 1 plus a. So we see the polynomial order convergence of the predictive error. Okay, now we take the logarithm of the left-hand side and right-hand side. We get this expression. So log of the predictive error is obtained by minus a over 1 plus a times log n plus some constant. So here we are neglecting the constant, but anyway, so we have this expression of the predictive error. Okay, so then you see that this is a scaling law. So this is a scaling law. Okay, and this is an illustration of the very simple analysis. The log of the predicted error is given by minus some constant times log n plus constant. So that can be depicted like this. The horizontal axis is the log n. The vertical axis is the log of the predictive error. We see this linear envelope. And if you fix the model size, the predictive error is given by this curve. So it looks like this. Okay. For different m, so we have a different curve. But for each sample size n, for each sample size n, so we choose the best model size. So then we get this this blue line as an optimal predictive error. Okay. Okay, so remember that in the experimental results, so we see this kind of curve, And so we have a linear envelope for the log of predicted error. For fixed model size, we see this curve. Okay, so this kind of curve is very similar to this curve. So therefore, classic statistics learning theory and very simple linear model can already explain the scaling law. Okay. So yeah, so anyway, so this is a statistical learning theory. So now we try to apply this kind of argument to deep neural networks. Okay. So instead of just a linear model, so we consider the deep learning. Okay. So so as we have seen, so the problem is that the analysis of a bias. Okay. If you can analyze the bias, so then so after that, just counting the number of parameters, so then we obtain the bias, so the variance term. So such a bias term is has been analyzed by many authors. For example, so these kind of well-known function classes like a Baron class and the Helder class and the Sobolev class and the Besov class. So many authors have analyzed the approximation errors by deep neural network models. So if you are interested in, please look at these kind of classic papers. Okay. So today I will talk some more recent results. Okay. So okay, so this is one of the one result from the classic papers. Okay, so let us consider a Sobolev class. Maybe Sobolev class is a little too complicated. So, but I explain intuitive way. Okay, so the function f in the Sobolev class is s times differentiable function. So more precisely, the norm of the Sobolev space is defined by like this. Okay, the Sobolev space is characterized by two parameters, S and P. So now, so you don't need to understand P. So the S is a more important parameter here. So S characterizes the smoothness of the function in the Sobolev space. So roughly speaking, the function f in the Sobolev space is S times differentiable. So therefore, if S is large, so then the function f in the Sobolev space is higher order differentiable. So that means that function f is smoother. Okay, so in that sense, S controls the smoothness of the target function f. So the function f is S times differentiable. So okay, so now we want to approximate S times differentiable function f by a neural network. Okay. Now, for that purpose, we consider this two-layer neural network with width n. So as the activation function eta, we consider activation function that satisfies this property. So that is eta is infinitely many differentiable in some open interval, and at some point b in the interval, so eta satisfies this condition. So that means that every derivative of eta at point b does not vanish. I mean, so for every k, the case order derivative does not vanish. So for example, if you consider sigmoid function, so then it satisfies this condition. But anyway, so for some smooth activation function eta, we can approximate the function f in a Sobolev space with this precision. So the approximation error is basically bounded by n2 minus s over d. So remember that S controls the smoothness for the function, and D is the dimensionality of the input. Okay, so this is a classic result. So yeah, so this means that the approximation error is basically characterized by the smoothness and the dimensionality. So this is one of the important notions of approximation errors. Okay, so the smoothness S, so S controls the smoothness of the target function, and D is the dimensionality of the input. So that are the important two quantities. Okay, so through this kind of analysis, so depending on the target function class, so then we have some bound of the approximation error. So then by analyzing the bias and the variance, we get some estimation error bound. Through such a non-parametric regression analysis, so we can show that the deep learning can be better than the kernel method in the non-parametric regression program. Okay, so of course it depends on the shape of the true functions. So we cannot say that deep learning is always better than the kernel method, but depending on the shape of the true target function, the true functions, so then the deep can be better than the kernel method. For example, if the true function is so-called in a reduced rank regression model, so deep can be better than the kernel model, kernel method. And if the true function is included in so-called piecewise smooth function class, so then deep can be better than the kernel method. And another example is that if the true function is in a Bezoff space, the so-called Bezoff space, then deep can be better than the kernel method. And if data has some low dimensional structure, so then the deep can be better than the kernel method. Okay, so I will explain these two situations because these two situations are kind of typical settings where the deep can be better than the kernel method. Okay. Yeah, here are some illustrations of these two situations. So, yeah, so one that in the Bezoff space settings, the true function in the Bezoff, the settings where the true function is included in the Bezoff space corresponds to this illustration. Okay, so in these situations, the true function has both a smooth and non-smooth part. So this is important. Okay, so it has some so the true function has some mixture of different properties. Okay, so it has a smooth part and a non-smooth part. So basically, this kind of function is difficult to estimate because the true function has some bump shape around here. So this kind of shape is difficult to estimate. The smoother function is easier to estimate. So actually, we have observed that. So if S is large, the rate of convergence of the approximation error is fast. That means if the true function is smoother, so then we get a better approximation error. So the same thing also happens for the non-parametric regression problem. Okay. So if the target function is smooth, so then it is easier to estimate. But around here, so depending on the location of the input, there appears some difficult point like this. So in this case, the deep can be better than the kernel method. Okay. Now let us consider kernel method. For example, if you, you use the Gaussian kernel, then the Gaussian kernel looks like this. Okay. So because the kernel method is a linear model, so it puts the kernel function like this. So they locate the in the kernel method, we locate the kernel function evenly on the input space, and we consider its linear combination. Okay, we approximate the target function by taking a linear combination of these basis functions. Okay, the point here is that the kernel function has the same width. So independent of the location of the input, the basis function, the Gaussian kernel has the same width. So therefore, it doesn't change the resolution, or it doesn't change the frequency. However, the target function has a different smoothness. So it is expected that it is better to change the width. Well, in other words, it must be better to change the resolution of the basis function. But however, if you use the kernel method, so you cannot change the width of the basis function. That means you cannot change the resolution of the model depending on the input X. Okay. On the other hand, if you use the neural networks, because neural network has internal layers, so it can extract the good features. So because of the feature extraction layers, so it has some adaptivity. In other words, it can change the resolution of the model. It uses a high resolution model around here. It uses a high resolution function around here. So then it can improve the approximation error around here. But on the other hand, so here is a smooth part. So it decreases the resolution of the model. So then it uses a kind of low resolution function around here. So the internal layers works as something like a constructing a basis functions. So then through the internal layers, it can change the resolutions. So it is called the adaptivity. Okay, so depending on the location, so it can change the resolution. So that can improve the efficiency. So the next question, next example is something like that. So the true function only depends on the few directions. Okay, so it doesn't it doesn't depend on other directions. Okay, so this direction is the informative features. So this direction is the non-informative features. But if you use the neural network, you can extract this informative features from the input, and it can neglect this kind of non-informative features. So then it can avoid the cause of dimensionality. However, if you use a kernel method, so there doesn't appear so feature extraction layer. So it cannot find an informative feature. So then it suffers from the cause of dimensionality. Okay, so here is the result. So first, let us consider situation in the left-hand side. Okay, as I said, that situation corresponds to the setting where the true function is included in a base of space. Okay, in these situations, the deep learning achieves this learning rate, where n is the sample size, and s is the smoothness of the target function, and the true function, and d is the dimensionality of the input. So this is a typical convergence rate of non-parametric regression. So if you will study the non-parametric regression, so I guess you will see many times this learning rate, this convergence rate. This convergence rate is very typical rate of the convergence in non-parametric statistics. And also, it is known that this rate of the convergence is minimax optimal. Oh, okay, so I'm considering the mean squared error. Okay, so the mean squared error, the rate of the convergence or the mean squared error is bounded by this quantity. Okay, so as the sample size n goes to infinity, so then the mean squared error should go to 0. So this is because if you have many data points, so then you can estimate the true function more accurately. So the mean squared error can be in other words, the predictive error can be bounded by this quantity. Okay. But on the other hand, if you use the kernel method, for example, if you use kernel-rich regression, so you suffer from the suboptimal rate, so which is given by this rate. So you can see that there is an additional term like this. So that this additional term is characterized by some parameter p. So what is p? The p is the parameter that controls the uniformity of the smoothness. Okay? If the target, the true function is not uniformly smooth, so then p can be small. Okay, so in other words, if the true function has this kind of bump shape, so then p can be small, and if the true function is uniformly smooth, so then p can be large. So but we can see that if p is small, so then this term cannot be neglected. So then there appears a huge difference between the kernel-rich regression and the deep learning. Okay, so I have some questions. Cannot something like a PCA reduce the dimensionality? Yeah, of course, the PCA can reduce the dimensionality. And how does that compare to deep neural network in the case of extracting lower dimensional multiple? Okay, yeah. Of course, the PCA is one method to extract features from the data. So the PCA is basically the linear method that can extract the features. But if you naively apply the kernel method, the inside the kernel method, there is no functional that can perform the PCA. So therefore, you should manually do the PCA, something like pre-processing. Okay, you cannot directly do the PCA, so during the optimization. So you do PCA, then after that you apply the kernel method. So it is like a two-stage method. It is already a kind of a deep neural network. Okay, the PCA is the first layers, and on top of that you perform the kernel method. So this is already a kind of a deep neural network. So of course we cannot distinguish the deep learning and the other methods. So anyway, so this kind of procedure is already a kind of a deep learning. Okay, and moreover, the PCA performs just linear projections. That is just a linear projection, and moreover, PCA neglects the output. So PCA is performed only by using the input X. So it doesn't see the output. Of course, there is some variant of PCA that is called sufficient dimension reduction. So that use the information of the output. But anyway, so PCA itself is just using the input only the input. So therefore, so sometimes it suffers from suboptimality. Yeah. So because PCA is something like a unsupervised method. So, but usually it is better to use a supervised method. So yeah, thank you very much. And so, okay, so I'm going to the next question. So may you explain how to compute S? Okay, yeah, okay, so you don't need to estimate S itself, okay? You don't need to know S itself, and just do deep learning. And then the important point is the configuration of the model size. Okay, so the model size can be optimized by using cross-validation. Yeah, or looking at the validation data, so then you can tune the model size. If you pick up the best model size, then you can achieve this learning rate. So therefore, you don't need to estimate S itself. Yeah. Okay. I guess it answers your question. Okay. Well, okay. So anyway, so okay. So you don't. So even if you don't need, even if you don't know the smoothness parameter S, by tuning the structure of the model, so the structure, the size of the deep neural model, so then you get this learning rate. So that is a good point of neural networks. Okay, so so as I said, so the kernel method doesn't have an adaptivity, so it doesn't change the resolution depending on the input. So then it suffers from this suboptimality. But the deep neural network can find the bump shape around here, so then it can change the resolution depending on the input. So then it can improve the rateable convergence like this. Okay, so I want to explain a little bit more about this result. Okay, here's a definition of the Bessel space. So I haven't defined the Bessel space, but it is defined by like this. So Bessel space has a close relation to the so-called Hilbert space and the Sobolev space, and it is formally defined by like this. But this is too complicated. So instead of explaining the precise definition of the Bessel space, so I give just an intuitive definition of the Bessel space. Okay. The norm in the Bessel space is defined by like this. The function f in the Bessel space should have a finite norm defined by this one. Okay. And so the norm of the Bessel space is given by like this. And also the Bessel space is characterized by the three parameters, S and P and Q. And here the important parameters is S and P. Okay. And S represents the same quantity as the Sobolev space. So the function f in the Bessel space is roughly S times differentiable. So therefore, S controls the smoothness. If S is large, so the function f in the Bessel space is higher order differentiable. That means the function f is smooth. In an extreme case, if S is infinity, so the function f is infinitely many differentiable. So it is very, very smooth. and so another parameter is P. So P is coming here. Okay, so the norm is basically defined by the LP norm of the S times differentiations. Okay, so if P is infinity, so this is L infinity norm. So therefore, S times differentiation is uniformly bounded for all the input X. So because this is a L infinity norm, L infinity norm is the same as a splimum norm. The splimum of the S times differentiation is bounded. So this means that the differential, the S times differential is bounded uniformly. So therefore, the function f is uniformly smooth. But if p is small, like p is 1, we take the L1 norm. So this means that we take the average of S times differentiations. So therefore, just an average is bounded. The average of the differentiation is bounded. Average of derivative is bounded. So we can only ensure that the average is bounded. So therefore, at some point, the derivative could be very large, but just taking an average over the all input X or input X. So then that could be bounded. So so therefore, if P is large, so then at some point function f can be deviated. Okay, so but if the function f is very smooth outside of that location, so then the average of the derivative could be small. So in that sense, P controls the uniformity of smoothness. If P is large, so then we have a uniform smoothness, and if P is small, then we have a kind of non-uniform smoothness. So that means, so maybe we have this kind of shape. So at some point, the function f deviates, but in an average sense, it is basically smooth. Okay. Yeah. So here is some illustration of a function in the Bessel space. If P is small, so there could be some rough part, but in average, it is smooth. So here's a smooth part. By taking its average, the function f is smooth. And if P is very small, if P is very small, if P is very large, and if the smoothness parameter S is small, like D over P is greater than S, so then there can appear the discontinuous point. Okay, if the function is the function f deviates very much, so then there can appear this discontinuous point like this. Okay, so therefore the Bessel space contains a discontinuous function. Okay. Yeah, so now we try to approximate the function f in a Bessel space by using a deep neural network. Okay, so let us consider the deep neural network with depth L and width W, and which can be expressed like this. And we also consider sparsity S. So this is just by a theoretical reason. So you can neglect this. So here I explain it in more details. Okay, we consider a sparse neural network where the number of non-zero parameters in the network is bounded by S. Okay, so many weight matrix, so many edges are 0. So the number of non-zero edges are bounded by S. So we consider this kind of a setting. Okay, so actually, so there have been some theories that works without this sparsity. But yeah, we put this condition. Okay, so B is not so much important. So non-bound B. So B means that each parameter in the neural network is bounded by B. Okay, so there are many parameters like weight matrix, but all of them are bounded by B. Okay, so this set, the set of neural networks with these conditions is denoted by FLWSB. Okay. And as for the activation function, we consider ReLU activations. We consider ReLU activation. Okay, so then we have this approximation bound. So, but this is complicated. So let us consider a much more simpler expression. So okay, so for any integer n, so let depth L and width W and sparsity S like this. So L is order log n, the width is order n, and S is order n log n. So then we have this approximation error. So that means for any true function f naught, that this is what we want to estimate. Yeah, this is what we want to approximate. So f naught is included in the unit ball of the Bessel space. And for any function f naught, there exists a neural network f check such that the LR distance between f naught and f check is bounded by n2 minus s over d. Okay, so this is the same as the rate of convergence in what we have seen in the previous slide. Okay, we have seen so n2 minus s over d. So the same rate of the convergence appears again here. Okay, so but here, so we don't need to assume the activation function eta is very smooth. So ReLU activation function is okay. Okay, so the approximation error is bounded by n2 minus s over d. So you can see that the smoothness and the dimensionality of the input affects the rate of convergence in the approximation error. Okay, so to show this kind of approximation error, so this is the typical steps of the proofs. Okay, so here is the proof strategy. So this is a very typical strategy to prove that kind of approximation errors. Okay, so first we find the basis function expansions of the target function. For example, if the target function in the Bessel space, maybe the true function can be expanded like this. Okay, so true function is given by the summation of alpha I psi I, where psi I is some basis functions. Maybe this can be the Fourier basis, or maybe this is a wavelet basis function. Anyway, we expanded the true function by using some basis function. And we pick up some n basis functions from this series of the summations, and we discard other parts like this. So then usually in some so function class, usually so there's some well-known function classes. So the norm of this redundant discarded part is bounded by n2 minus s over d. Okay, so we remain only n terms, and we discard other terms, and this term is bounded by n2 minus s over d. For example, in a Bessel space, we can show this kind of thing. Other example is the Sobolev space. As for the Sobolev space, we can also show this kind of bound. Okay, so after that, so we approximate each basis function psi I by a deep neural network. Okay, so for each input, so from the internal layers, we have many outputs. So the output from each neuron corresponds to the approximation of the basis function. Okay, so maybe so the output is psi hat 1 to psi hat n, where width is n. So then each output from the internal layer corresponds to the approximation of each basis function. Okay, so then we show that the psi I can be well approximated by deep neural network. Then finally, we take its linear combinations. So okay, so we're taking the linear combination of the output, so that can be also realized by deep neural network model. So that is the approximator. Okay, so then combining these two evaluations, so then we have this approximation error bound. The first term is coming from this approximation error. And basically, so this approximation error can be bounded by exponential to minus depth. So if the depth is very large, so then this approximation error becomes very small. So this is because deep network has an exponential explicit power. Okay. So then the second term is coming from this term. So it is basically bounded by the polynomial order to the number of basis functions n. Okay, so then we obtain this rate of the convergence. So as for the Bessel space, so we can employ the so-called cardinal B-spline basis function as a basis function. Okay, so as a basis function of psi I, so you can employ the so-called cardinal B-spline. Okay, so this is a little bit very detailed, so I don't spend so much time here, but anyway, so that is formally defined by like this. So here nx is given by this step type function. This step function is given by nx. We compute its m times 1th order convolutions. This is called cardinal B-spline of order m. Okay, so depending on the smoothness parameter s, we set the order m. So if s is larger, we set m is larger than s. So we set the order m to be larger. Okay, so anyway, so the cardinal B-spline looks like this. The first order cardinal B-spline is this one. The second order cardinal B-spline is like this. The third order cardinal B-spline is like this. So this cardinal B-spline of order m is a piecewise polynomial with order m. So this is a piecewise polynomial. Okay. Okay, so by using this B-spline, and we can define a so-called wavelet basis function. Okay, by using such an wavelet basis functions, we can expand the function f in a Bessel space like this. So here nkj is basically the cardinal B-spline function. So more precisely, is a tensor product of a cardinal B-spline. For each input xi, so x is a d-dimensional. For each coordinate xi, we calculate a cardinal B-spline. We take its product from I equal 1 to d. So this is basically the tensor product. And moreover, we consider a different scaling and a different shift, different locations. Okay. So then from one n basis functions, one B-spline basis functions, you can create many basis functions. Okay, you can change the scaling, and you can change the location that the cardinal B-spline is put. So then you can generate many basis functions. So this is called wavelet expansion, or wavelet basis functions. Okay, so by using this wavelet basis, we can expand the function f in the Bessel space like this. Okay, so and so we can show that by picking some appropriate n terms from this wavelet expansions. So then we can show that the residual is like n2 minus s over d. So this appears in the approximation error bound here. Okay, so after that, just we need to show that this cardinal B-spline can be well approximated by the deep neural network. So then we can conclude the proof. Okay, so interesting point here is that, so as I said, so the neural net, the function f in the Bessel space can be expanded by using this wavelet expansions. Okay, so and also there is some norm equivalence like this. So suppose that f is expanded like this by using the coefficient. The norm of the Bessel space is proportional to the norm of the coefficient, okay, like this. But this is very, very complicated. So you can see that this is like a LP norm of the coefficient. So you can neglect all of them. So this is just so the essence is that this is just an LP norm of the coefficient, which is given by like this. Okay, so remember that the unit ball of LP norm is like this. If P is 2, the unit ball is like this ball. And if P is 1, the unit ball is this kind of shape. And if P is smaller than 1, so then the unit ball of the LP norm shapes like this. This is no longer a convex set. So then maybe you know that the small p corresponds to the sparsity. So if you know the sparse estimation, so we usually use L1 norm to induce a sparsity. So then you also see the sparsity here. For example, if p is 0.5, and if alpha 1 is very large, so then alpha 2 is almost 0. If p equals 2, so then even if alpha 1 is here, then alpha 2 can be large. So now we are assuming alpha 1 and alpha 2 is included in this unit ball. And in that case, so then if alpha 1 is sufficiently large, so then alpha 2 is almost 0. So if p is 0.5, but if p is 2, so then alpha 2 is not so close to 0. Okay. So on the other hand, if alpha 2 is large, so then alpha 1 should be very close to 0. So therefore, if p is small, so then if some coefficients are large, so then other coefficients should be small. Okay. If one coefficient is large, then the other coefficient should be 0. And if one coefficient like alpha 2 is large, so then alpha 1 should be small. So if p is small, so then there appears sparsity. So now we turn back to this wavelet expansion. Okay, if p is small, so then the many parameters, many coefficient is close to 0. For example, the coefficient corresponds to the basis function, and here is 0. So then the high resolution components are 0 around here. But maybe, so around here, the coefficients are not non-zero. So then around these locations, so then there appears a high frequency component. Okay. Okay, so the horizontal axis is x. So if alpha kj, so the coefficient are 0 for the basis function around here. So there doesn't appear the high frequency component. But if the coefficient here is non-zero, so there appears a high frequency component. So therefore, if p is small, so then sparsity corresponds to the uniformity of the smoothness. Okay. So yeah, so if p is large, so then the alpha kj, so the coefficient is the coefficient are not sparse. The coefficient are not sparse. So then there doesn't appear the imbalance of the smoothness. But if there appears sparsity, so then there appears an imbalance of the smoothness. Okay. So here we see some connection between the smoothness and the sparsity, and more geometrically, we see the connection between the convexity of the model and the sparsity, convexity of the model to the smoothness. Okay. So if p is small, so then the unit ball is non-convex. And if P is large, so the model is more like a convex. So this kind of geometric consideration is becomes important in the later on. Okay. So anyway, let's go back to the approximation error, which was given by like this. Okay, now we compare with this one by we compare this one with some other approximation method. For example, non-adaptive method. Okay, so let us consider non-adaptive approximation method. So where we predefine, pre-specify the basis function. Okay, we prepare any basis function independent of the target function, and we fix this basis function like a kernel method. And we take its linear combination, then we approximate the target function. This is called the non-adaptive method. But if you use a neural network, it can change the resolution with the basis functions through the internal layers. And so it can change the resolution depending on the input X. So this is called the adaptive approximation method. Okay, so as long as you're using non-adaptive approximation method, the approximation error can be bounded by like this. You again see a difference like this, 1 over P minus 1 over 2. So if P is small, so then this term is large. So the difference between the adaptive rate and non-adaptive rate becomes very large. Okay, so this is because adaptivity. So in terms of function approximation ability, selecting a good basis function depending on the target function is very important. So, and we can see the neural network can do that. Okay. And so finally, so we consider the estimation errors. So as we have considered, so the estimation error is decomposed into bias and variance. The bias has already been analyzed like this. And as for the variance, so through some calculation of the log over the covering number, so we can show that the variance is bounded by basically the number of non-zero parameter S times depth divided by sample size N. So yeah, basically the sparsity, the number of non-zero parameter S comes here. Okay, so then by balancing the bias and the variance, by substituting the bias to here, then you get the optimal estimation error. Okay, so we can balance the bias and the variance, then we can obtain the optimal the size of the model. Then we have this rate of convergence over the estimation error. Okay, so here we are looking at just estimation error instead of approximation error. Okay, so we consider the least squares estimations in a set of a neural network model. Okay, so we assume this optimization can be executed. So we don't consider optimization program here. So then that estimator is obtained by like this. The empirical risk minimizer satisfies this rate of convergence, where small n is a sample size. Okay, and so the good thing is that this is almost a minimax optimal. Okay, so what is the minimax optimal? So this is also an important notion in statistical learning theories. The minimax optimality is given by like this. Okay, for any estimators, so we consider a worst case error. We take the worst case among the set of true functions, where the true functions the true function run in the unit word of the vector space. And in this set, we take the worst case error. Okay, so this worst case error is lower bounded by n2 minus 2s over 2s plus t. You can see that this lower bound is same as this upper bound up to some polylog n orders. If you neglect the polylog n orders, so this upper bound is the same as this minimax optimal rate. Okay, so this statement gives a very strong result. Okay, for any estimators, even if you are, even if you know, well, strongest estimators. So maybe suppose that there exists the strongest estimators. So that kind of estimator, even if you are using such a strongest estimators, you cannot overcome this rate of convergence. Yeah, so this can be shown by using some information theoretic tools like a Fanos inequality and the so-called Balshamov-Gilbert inequality and something like that. more details can be found in these books. So, for example, the Chiba Cox's book is very useful, and there is also another paper, Ginny and Nick's book. So this is very thick paper. So, sorry, thick book. So this is a very huge book. So maybe it is difficult to read, go through the whole contents. But so in this book you can find many techniques to obtain this kind of minimax or lower bound. Okay, so then next, then next we look at, so we restrict ourselves, we restrict the set of the estimators to some specific estimators, like a kernel-rich regression, something like that, okay? Okay, so we are interested in the comparison between deep neural network and the other estimators. So we consider some restricted estimators. Okay, so the kernel-rich regression is given by like this. So this is obtained by solving the least squares estimation. So more precisely, regularized least squares estimation. So then we get the kernel-rich regression estimator like this. So the important point here is that the kernel-rich regression is linear to the output y. Okay, so then this is called a so-called linear estimator. This is called a linear estimator. Okay, so the linear estimator does not mean it is a linear to the input x. It can be non-linear to the input x, but it is linear to the output of the observations yi. So it is linear to the yi. So we have n data points xi, yi from I equal 1 to n. For each data point, we have an output yi. So then if the estimator is linear to this output yi, so then this is called linear estimators. So this class of estimators include other important estimators like a Nadaraya-Watson estimator and the k nearest neighbor estimator and the kernel estimator. Okay. So now we compare the minimax optimal rate of the linear estimator with the rate of the convergence for deep learning. Okay. So we consider this minimax rate in the linear estimators. So then we can show that the lower bound is given by like this. Okay, here is some additional term. So then this makes a difference from the deep network. Okay, so here's the comparison. So as long as you are using linear estimators, so the estimation error is lower bounded by this quantity. But on the other hand, if you use deep learning, so you get this nearly minimax optimal rate. So if p is small, so then this difference is significant because this term is non-negligible. So the rate of convergence for the linear estimators can be slower than the deep learning. Okay, so this is because of the adaptivity of deep neural networks. Okay. So now, more generally, so we can extend this result to more general settings, right? So then there appears a so-called convex Hull argument. Okay, so this is another new concept. Okay, so there appears a convex Hull argument. So roughly speaking, a function with a property that is destroyed by a convex combination is harder to estimate by a linear estimator. Okay. So the convex combination is a very important notion to characterize why linear estimator can be outpowered by kernel method. Okay, so here is one example. So let us consider a so-called piecewise constant function with 3 jumps. This is a very simple function class. So this is a piecewise constant functions, and there is a 3 jumps. We know that there is a 3 jumps, but we don't know the locations where the jumps, where the jumps are. Okay. So we take a convex combination of this function and this function. So both of them are included in this function class, but the convex combination can be outside of this function class. So therefore, this function class is not closed under the convex combinations. So actually, by taking the convex combination of this function, you have a function with six jumps. Okay. So this is outside of this function class. Well, so yeah, so anyway, so this function class is not closed under convex combinations. So for this, if the target function class is not closed under the convex combination, so then there appears a difference between deep method and the kernel method. If you use the deep learning, so we obtained 1/n convergence rate over the estimation error to estimate this kind of function. But if you use the kernel method, you obtain 1 over square root n convergence rate. Yeah, so there is a square root n difference. Okay. So so this is because convex Haar argument. So I should explain that in more details. Okay, so the convex Haar argument can be written by this equation. So we have considered the minimax optimal rate for the linear estimators. The minimax optimal rate is the same as the minimax optimal rate on the convex Haar of the target function class. Okay, is it okay? So the worst case error is taken in the target function class F. But as long as you are using linear estimators, so then we should take the worst case error in the convex Haar. So if the target function class is very much non-convex like this, so then the convex Haar could be much larger than the original function class. For example, so this function class is highly non-convex. So therefore, by taking its convex Haar, so its convex Haar could be much larger than the original function class. So therefore, this prima becomes very large. So then there appears the difference between the deep and the shallow method. So this is an important notion. This is a little bit more geometric notions why deep can be better than the kernel method. More precisely, we can extend this result to so-called Q-Haar instead of precise convex Haar. So we can consider this kind of a Q-Haar, but I omit some details. Okay, so let's turn back to the settings of Bessel space. We have noticed that if P is small, so then unit ball becomes like non-convex set. That becomes non-convex set. So then by taking its convex Haar, it becomes larger. So therefore, in that case, the linear estimator suffers from the suboptimal rate. Okay. So therefore, so this theory can explain the failure of a kernel method for other situations in a unifying manners. Okay. So this convex Haar argument can explain many other situations in a unifying manner. So yeah, so we have already obtained some kind of well, unifying framework that can explain so why deep can outperform the kernel method. Okay, so next, so I want to go one example that can be explained by this framework. Okay, so that is about the dimensionality. Okay, so as I said, the rate of convergence in the non-parametric regression is characterized by the smoothness and the dimensionality. So next, we consider the dimensionality. I quickly go through this section. Okay. So a similar thing also happens here. Okay. So as I said, this is a minimax optimal rate in the Bessel space to estimate a function in the Bessel space. So then, but the dimensionality D comes here. So therefore, if the dimensionality D is large, this rate of convergence is very slow. So this is called the curve of dimensionality. So this is called the curve of dimensionality. So there is some exponential order dependency on the dimensionality D. But in reality, in the deep learning is performing good performance. The deep learning gives a good performance for example, the image data set. The MNIST data set is 784 dimensionality. This is very high. If this dimensionality is coming to here, then the rate of convergence is terribly slow. So this is not realistic. Okay, so but why the deep learning can work well in such a high dimensional settings? Okay, to explain that, there is a so-called manifold regression analysis. Okay, and so the intuition is something like that. So the data is distributed on some low dimensional manifold, say the capital D dimensional manifold. So then the rate of convergence is characterized by capital D instead of the small d. The small d is the dimensionality of the whole space, but the capital D is the low dimensional manifold on which the data is distributed. So therefore, if data is distributed on the low dimensional manifold, so then the rate of convergence becomes much, much faster. Then it can avoid the curve of dimensionality. Actually, it is experimentally investigated that the MNIST data set has a 13 or 14 interesting dimensionality. So that is the capital D is 13 or 14 instead of 784. So this is a pretty good. So compared with 784, so 13 or 14 is much smaller So this is a reasonable number. So it can be coming to here. So yeah, so therefore this kind of theories can explain for why deep can work well in the high dimensional setting. So this is called a manifold regression. Okay, so but one difficulty or drawback of this kind of analysis is that so data should distribute it on exactly on the low dimensional manifold. It cannot be outside of a low dimensional manifold. So, but what happens if the data can be noisy, or so maybe so you can apply some data augmentation, so then data can be easily outside of a low dimensional manifold. So what happens in that situations? So to deal with such a setting, so we can consider the smoothness of the target function. That means the target function has a smoothness, has a different smoothness depending on the directions. Okay, the function, the true function is not smooth to this direction. The true function is not smooth to this direction, but the target function is almost independent to this direction. This direction is perpendicular to the submanifold. So then, so the target function is almost constant to this direction. So in mathematical sense, the true function has smoothness S1, S2, and S3 to each directions. And so the smoothness has this kind of relation. So S1 and S2 is much smaller than S3. Okay, the smoothness to the third coordinate is very large. So it is almost constant. The constant function is very smooth. So because its derivative is always zero. So that such a constant function is very smooth. So S3 should be very large. Okay, so if we consider this kind of situations, so maybe so we can deal with a setting where the data is outside of the manifold. Actually, that kind of a situation can be captured by so-called anisotropic vessel space. So the anisotropic vessel space is characterized by D positive reals S1 to SD. Okay, so instead of one real variable, so S1 to SD are coming here. So SI represents the smoothness to the ith coordinate. And so for example, S1 represents the smoothness to the first coordinate. And it is S2 times differentiable to the second coordinate. So then we can define the smoothness depending on the directions. Okay, so and the P also works. The P also plays the same role as the previous slide. So P controls the smoothness, the uniformity of the smoothness. So then. Okay, so I skip some details. So finally, so we obtain this rate of accommodateness. If the true function is included in the anisotropic vessel space, we get this rate of accommodateness. So if it is included in the normal vessel space, we have this rate of accommodateness, but the D appeared, so the curve of dimensionality appears. But if you use an anisotropic vessel space, if you use that if the true function is included in the anisotropic vessel space, so then we can show that the rate of accommodateness becomes like this. So instead of S and D, there appears S tilde. So S tilde is defined by like this. The S1, the summation of S1 inverse to the SD inverse, and we take its inverse. This is a kind of reciprocal sum of the smoothness to each directions. Okay. So if S1 is small and the other parameters S2 and SD are very large, and it is almost, so it only depends on the one direction, the other toward the other direction, it is almost a constant. So then S tilde is almost S1. So then instead of S tilde, there appears S1. So dimension D doesn't appear. So this means that the neural networking avoids the curve of dimensionality. Okay. Okay, so so next we compare the rate of convergence for the deep network with linear estimators, where the setting is something like that. The true function only depends on the capital D subspace. Okay, so in the first layer, so we project X to the subspace by using some matrix W, and on top of that, we put function G, which is included in the vessel space. So then the F naught is also included in some composition of the anisotropic vessel space. So then the rate of convergence becomes like this. Okay, so instead of small d, the capital D comes here. But if you use a linear estimator like a kernel method, and then the small d comes here. So I don't show the proof of this bound, but anyway, the minimax optimal rate of the linear estimator is rho bounded by this quantity. But the small d comes here, so then it suffers from the cause of divisionality. So this is because the deep learning can find such an informative directions. Okay, so then the deep can avoid the cause of dimensionality, but linear estimators cannot find the informative directions, so then it suffers from the cause of dimensionality. But if you use, even if you use the principal component analysis or the PCA, but it cannot perform this rate of Okomatis because so in this setting, so X can be uniform distribution on the 0, 1 unit cube. So there are no principal component. So if you neglect the output, so then it cannot find the good directions. So therefore, so the deep learning do that in a supervised way. But if you use, but even if you apply the PCA, it cannot find the informative directions. So because it doesn't use the output, the information of the output Y. So yeah, so therefore, in that sense, that using a kind of supervised information is very important to achieve this rate of commonness. Okay, so then I want to finish the representability section here. If you have any questions, or I want to take it. Okay, no questions. Okay, okay, so I have another 9 minutes. Yeah, but okay, so as for these sections, so okay, so next I want to talk about some generalization error of the over-parameterized network, but I think I cannot finish it in 10 minutes. So it will take 15 minutes or something like that. So okay, so maybe it is better to stop here. Okay, so then tomorrow I will talk about this section, so generalization ability of over-parameterized network, and then the main part will be the optimization. Tomorrow's contents, the main contents will be the optimization.